So first of all, can you hear me the end row and the last row here? Yes, very good. So we are going to shift the focus in this talk from running applications and doing monitoring to running relational databases on Kubernetes. And the low mark goal of my talk is to persuade you that this is not a crazy task. The regular goal is to actually give you some ammunition in a form of services, the open source services that you can use in order to accomplish this goal. And the blue sky is to actually demonstrate you that all those things work by giving you a live demo, which is always exciting because sometimes it works, sometimes it's not, and depends on many factors. One of the things that I want to mention is that I will accept questions afterwards, as everyone else during this presentation. I usually love to have questions during the presentation, but this is how it works here. So if you have some interesting questions, I would be happy to answer it either afterwards when we have time, or if you don't have time now, then when we have a coffee break or a beer break or some other kind of break. Yeah, the title is Postgres Scalability on Kubernetes with Patroni, and I will tell you what is Patroni during this talk. The guy who is speaking in front of you, my name is Oleksii. People at Starbucks call me Alex. This is also how I'm known. I'm a database engineer at the German company called Zalando. I'm doing Postgres for almost 15 years. Been even listed as a contributor to Postgres. I've recently started working with modern technologies like Kubernetes and Docker and so on, and therefore I am here talking to you, the DevOps crowd. I'm mostly a software engineer, never considered myself a DevOps or DBOps or some other kind of ops. So I have a Twitter, and on this Twitter I will share the slides of this presentation. I'm pretty sure they will be also shared by other means. And I also have an email if you just want to ask me a question directly. Who of you knows what is Zalando? Sorry, my clicker is... Yeah, good. Who of you doesn't know who is Zalando? Sorry, I missed the first round of hands. Okay, not so many. Zalando is a big fashion retailer. On my initial slides, we had 15 countries, but ours we launched in 2 more countries, and I had to redo those slides and redraw those maps. And we are present in Poland since 2013. We have billions of revenue. I wouldn't tell you how many billions because this has to be always coordinated with our marketing team, and you probably don't care about that. What you do care is what is the topic of this talk, how many databases we are running. And we have quite a few database clusters spread over different environments. The traditional data center, which has been the first environment that we ran it, then we migrated to AWS. And recently in 2017, we started to run databases on Kubernetes and developed some tools to help us, which is basically the title of this talk. Let's start with names, because names are important. In database world, cluster is so overloaded as a term. You can people name call different things by the name cluster. And in my talk, I'm going to tell that Postgres HA cluster is a system that consists of one primary and multiple replicas. And an individual node will be called Postgres instance. And in Postgres, this Postgres instance can have multiple independent databases inside. So we have the HA cluster, we have the instance, and we have databases running inside that instance. Yeah, probably will. So one thing is, few words, why did we choose Postgres? We are running Postgres since 2012, trusting our clients' data, our own data, payments. Every major piece of data is trusted to Postgres, and not less because Postgres is a consistent database, and if you are working with client data and with payment, demand no less than strong consistency. But also because there is a transactional DDL, and there is also sophisticated transactional system inside Postgres. A lot of people refer to databases as a data storage, as a data store. but Postgres is much more than a data store. If you are running multiple transactions concurrently and you have to figure out what is the result of this concurrency in your application, then you are doing things in absolutely wrong and a complicated way, because this is the task of the database to do this. And due to Postgres true serializability and very good transactional support, this is very easy and makes application developers' lives also very simple. Extensibility, because you can create new custom types, you can create custom indexes on those types, you can even create custom Postgres processes, for instance, for monitoring, and this is also what we did, is something that we really value in this database. But one of my favorite topics is Postgres community, because if you have a bug in Postgres, it's always happening that in the course of 1 to 2 days, the bug is fixed, you get a patch, you apply a patch, and continue working. Bugs are not that frequent, but the response rate, the response time, the how fast the community can address those things is really awesome. And this is the picture from the conference in Warsaw. The big European conference in 2017 happened in Warsaw. And the next one will happen in Lisbon, so if you want to join, I really encourage you to do so. But let's move to the main topic. So Zalando, how did we come to the current state of things, and from where did we go? This is basically how we scale things from small to big. And initially we had 2 different environments. So we had the main environment that is a traditional data center. We had 2 data centers, one in West Germany, another one in Berlin. Those were replicating between each other. We had primaries and standbys in the primary data center, and we had delayed standbys in the other data center, just in case someone drops a very important table and needs to restore it quickly. Then we will go to the delayed standby and do this. However, there were some issues with this traditional data center. One of those is if you needed to get one more server, it could take us basically months to get what we need, because this is hardware that has to be bought. Sometimes it's not available, sometimes it's not mounted correctly, and so on and so forth. So we could not really scale as fast as we wanted. The other issue was there was no automatic failover built in Postgres, so we had to have a the database team had to be on call in case hardware dies, there is a Linux kernel panic or something like that. Someone gets called, wakes up, repairs the server manually. Usually takes like 5-10 minutes. During these 5-10 minutes, sometimes orders cannot go through. The company loses money. No one is happy. So in 2015, the whole company moved from these traditional data centers to the cloud-based deployments based on AWS. And on AWS, we also run databases. So we run things on EC2 instances inside Docker container based on our custom platform as a service that is called Stoops. And they are basically also replicating data to S3 segments. So it kind of works for us pretty nicely, and eliminates the issue of we cannot get new servers, because on AWS you can always span a new server in several clicks and boom, you get a new database. The good question that is sometimes asked to me is, should you run your database inside a container? Well, there is a downside, because container is an overhead on your system, so it takes some CPU time. But there is also an upside, as you basically get reproducible deployments, because your dependencies are inside a container. If you want to run the same database with the same set of extensions on your local machine, you just run the same container on your local system. So containers gives us a lot of things that, for instance, Chef and Puppet give in traditional deployments. And because our platform as a service demanded to be used with containers, so we basically have a requirement that every application has to run in the container, and Postgres is not exception. We also had no choice but to adopt containers and find all these nice excuses of why we're running Postgres in a container. And how do we do this? I missed a slide, yeah. So we do have a container that is called Spiller. It's a Docker image. It doesn't run Postgres data directory, of course, on the Docker file system. That would be insane. It instead uses either EBS or i3 local storage to run Postgres to store Postgres files and then mounts this volume. It is configured using environment, so all these parameters, for instance, for Postgres can be passed with environment variables. We have a rule in this Stoops platform as a service that we only have one container per EC2 instance, so we never share the same instance between multiple Postgres installations, so we don't have this noisy neighbor problem. We pack their multiple Postgres versions from 9.4 to 10, but nevertheless the size of the container is very small. It's only 67 megabytes because we actually compress the image when we build it and decompress when the image is run, and that includes a lot of extensions from PostGIS to timescaledb to almost all possible extensions that can be practically used. And the image is open source, you can get it, it's on GitHub, and you can use it, you can even run it locally on your laptop. So what is the schema on AWS? How do we run things? This is still not the state of the art. This is basically like a bit historic image. So we run databases in Frankfurt region in 3 availability zones. One is primary, 2 are secondaries normally. So even if we lose the primary, we still have the high availability setup with one replica. We direct clients using the Elastic IP address. We used to have load balancer for that, but load balancer costs you $20 and Elastic IP is less expensive. So we get rid of it for primaries. For secondaries, we still use the load balancer, ELB, because you might have multiple replicas, and for that you want to do round robin between those replicas. We use Postgres in a Docker container. We use user data to pass all environment variables. We use S3 to ship WoW files and base backups. So in case everything goes down, we still can restore databases from this base backup, and we can even restore it to a certain point in time using the Postgres feature called point-in-time recovery. And we also have etcd deployed, which I will cover right away. So how comes that we can run those databases on AWS, which is known to shut down your instances from time to time? How comes that we can trust our sensitive data to that setup? So the secret sauce of us, the secret ingredient, is called Patroni. At some point we decided that we cannot live without automated failover, and basically all automatic failover solutions out there are not good, and we decided to write our own, and this is what we wrote. It's called Patroni, and it is based on the idea of oh, I want what Patroni is. Oh, wow, that was unexpected, sorry. Well, yeah, so Patroni is automatic failover solution, like many others, but unlike many others, it stores the information about the cluster in a distributed consistency store, which is also called DCS, and this is the abbreviation that we invented by ourselves because there was no abbreviations in place. So what is DCS? It's basically a key value store that is distributed, so there are multiple nodes there, and they keep the consistent state between themselves. So if there are nodes A, B, and C, and you write to nodes A and C, both nodes will see the same picture. And this is very important for us because what we store in this consistency store is the information about the cluster, who is the leader in the cluster, and what are the members of the cluster. So it's very important that all nodes in the Postgres cluster see the same picture. And basically Patroni decides for new nodes whether to initialize the whole cluster, the whole availability cluster, or to join an existing one based on the cluster name. For running instances, it monitors when the master goes down, because there is a key associated to the master or the primary node in DCS, and when this key disappears, Patroni decides that the master disappeared and does promotion. And it has a number of additional features. For instance, you can do time-based restarts. You can also schedule failovers. You can reinitialize nodes. You can have pause mode. You can recover the previous primary node that became replica and wants to join the cluster using pgrewind, and many more. So it's feature-packed. how Patroni works is it always manages individual instance. So if the cluster has 3 instances, each instance has Patroni attached to it. It's basically backed in our Docker image, and each Patroni manages only this individual instance. So it always decides for this individual instance whether this instance should promote or should continue to run as it is, or should demote in case this instance is a master. It should not be a master anymore. So what Patroni is not doing is it is not a global manager. It's not an arbiter for the whole cluster. It's not like we have only one Patroni set up for the whole cluster, and when Patroni goes down, the whole availability stops. No, there is one Patroni attached to individual instances, so it is still highly available. It's not doing every Postgres maintenance tasks that can be imagined. It doesn't do auto vacuum for you, it doesn't do reindex for you, and many other tasks that are usually performed by system administrators. It doesn't do. It's not a substitute for proper monitoring. There could be still issues when the replica, for instance, cannot connect to the primary because the primary doesn't have enough row segments. So the row segments that the replica asks from the primary are not there. And that situation can only be monitored from the database logs. So if no one is monitoring the logs, you might have these stale replicas, and Patroni won't be able to help you with that. Well, it's not a silver bullet, obviously. There is no silver bullet. And also, it's important that it's open source project, but it's not only developed by Zalando. It's developed by people around the world. There is Red Hat Project Atomic. There are consulting companies in Europe. There are even some governments that are using Patroni for their own things. So there are a lot of different developers from all over the world helping us to make Patroni a first-class availability solution, and it is backed in our Docker image in Spiro, and therefore this is how we use this on AWS. So why do we need distributed consistency? It's a very important slide. Imagine that we have leader election. The master went down, and now we are trying to figure out which node is a leader. So each node has Patroni attached, and each Patroni examines its own state. It looks how far is it from the previous leader. Because we are using asynchronous replication, it could be that the replica that has been examined are not exactly on the same position as the leader. It could be a bit far away. Some changes did not make it to that replica. So every replica looks at itself and looks at its neighbors and compares its own position with the position of the neighbors, and the replica that has the highest position decides to promote itself to the leader. But before doing promotion in Postgres terms, it first acquires the log in the distributed consistency system, in DCS. So it's pretty common that several replicas at once find out if their positions are equal, tries to acquire a log at the same time. And what we need from the DCS is the ability for the first replica to acquire that log, and the other replicas will basically fail to do this, and therefore we will have only one primary node. If that would not be true, then we would have multiple primary nodes, have a split brain, and then we would have to merge things manually, which is absolutely what we want to avoid. By relying on these compare and set operations and the properties of etcd or other DCSs, we can make sure that there is only one master at a given time and the leader elections are possible. That is why we need distributed consistency. It's a hard problem. We are not thrilled to solve this problem by ourselves, as other smart people already did so with etcd, Consul, Zookeeper, and as therefore we just piggyback on what they wrote and use their solutions instead of rewriting things from scratch in Python. This is the GitHub address for Patroni. You can go there, you can download it, you can file an issue if you see it doesn't work. There's also a documentation, some other presentations, so it's pretty good, has pretty good coverage on how to use it. And now we are coming to the state that we have now. At some point, we decided that just running on AWS is not fun enough, and we moved to Kubernetes. Well, fun is not really a reason for that. The real reason is that we wanted to save money, as we had a huge bill on AWS, and Kubernetes actually manages resources for you, and we decided to use that feature. But first of all, who of you knows what is Kubernetes and have any experience with it? has an experience with it? Oh, quite a lot of people. So just a brief list of bullet points for those who doesn't. It's basically, I cannot define it in one sentence, but it's all an open source components to manage your infrastructure. It's a Docker orchestration system. It's a hardware isolation layer. So if your application talks only to Kubernetes, it doesn't matter whether it runs on AWS, on Google Cloud, on DigitalOcean, or on any other cloud system. And you can actually port it from one to another quite easily by just relying on Kubernetes itself. It's also providing infrastructure as a code, so to say, because all resources that you describe are just YAML manifests that are at least pretty easy to read, if not to write. And for me personally, it's kind of a next step after these orchestration systems like Puppet or Chef, because it doesn't only helps you to deploy your applications in a reproducible way, but also helps you to maintain them running and manages resources for you. So what Kubernetes is not an operating system. It's based on Linux mostly with the containers. It's not a magical way. If someone tells you that they scale their infrastructure by deploying Kubernetes, ask them how. Because it's not a magical way to scale infrastructure. It's a tool, but you have to use this tool, and you cannot fire your DevOps team, which is yay, good for us because we are DevOps, at least most of you, because you still have to configure it, and configure it correctly is not an easy task. So if you think, oh, this is a shiny thing, I'm going to use it for my home website with 3 servers, probably it doesn't worth it. It's good if you have like 10s, 20s, hundreds of servers, if you have the whole like infrastructure as a cattle, not pets, meaning that you don't know your servers by name, and you basically say, I want to scale up my application on 20 servers, and please deploy these servers automatically. This is where Kubernetes shines, and this is exactly the use case of Zalando, because we have quite a lot of different microservices running on all sorts of servers, and we have databases, and we have queues, and all this stuff that has to be run on Kubernetes. So we naturally try to adopt it, and the infrastructure team said, now we are moving to Kubernetes, and we said, well, yeah, okay, now we are going to figure out how to move databases to Kubernetes. And this is what we did. So just another slide to compare what we have in the traditional infrastructure to what we have in Kubernetes. This is all invented by me. You may think this is wrong. If you think this is wrong, you can ask me afterwards. So even in traditional infrastructure, you have a physical server. In Kubernetes, you have a node. On a physical server, you may have virtual machines. On Kubernetes, you have pods. Each virtual machine may run one or more applications. Each pod may run one or more Docker containers. You may have your data on the external storage on the NAS or SAN in the traditional data center. In Kubernetes, this is translated to persistent volumes. You may have a load balancer to balance your requests between those servers. In Kubernetes, you have services and endpoints to do the same. If you have a big infrastructure, you probably have an application and hardware registry which answers the question on which server a given application runs. In Kubernetes, there is a rich metadata in terms of labels and annotations that also help you to do the same. Basically, you can query your pods or nodes or other resources by those labels. And you probably know about password files that you use in the traditional infrastructure to store, for instance, database passwords. In Kubernetes, there are special objects that are called secrets that are essentially doing the same thing, although in a more secure way, because you can have a fine-grained access to those secrets. They are like key values, storing keys and basically usernames and passwords. So this was basically a prelude to what we want to what I want to show, and this is how the declarative resource description looks like. It's a manifest, it's a simple YAML manifest. In this case, it describes a service that needs to run Nginx. This service, the Nginx, runs on port 80, which is listed here. It has to have some labels, and this is pretty straightforward. The same manifest also described all other resources on Kubernetes. Basically, they differ in what kind of resource in all these fields, but the idea is the same. You write those manifests, you get them to Kubernetes, and Kubernetes translates them to actual resources running in your cloud environment. Or maybe not cloud, because Kubernetes also works in a traditional data center. So the main question is, how did we build a Postgres cluster on Kubernetes? Basically, the traditional way is to use a construction in Kubernetes that is called stateful sets. Do you know what is stateful sets? Who knows what is stateful set? quite a lot of people. It's a controller that binds your pods to persistent volumes. So if your pod dies and then comes back, it comes back with the same persistent volume attached. And this is very convenient for databases, because in database case, you have your data directory on the persistent volume on the node, and then if the node goes down and then comes back, the node comes back together with this data directory mounted. Postgres starts and continues working as nothing happened. Of course, you can just run your databases like this. Have a stateful set with n nodes. One node is a primary, and other nodes are replicas. They are like fixed, so when the primary dies, after some time it gets up and mounts the volume and continues to run, and everything is fine. You don't have to write, you have to write almost no code. Unfortunately, it has some downsides. The downsides are sorry. Let's move it. The downsides of that is that it might take quite a lot of time to mount this persistent volume, like 3-5 minutes, because of the bugs in Kubernetes, because of the bugs in the planner, in the node provisioner. So during these 5 minutes, your database will not be available. And if the whole goal of your setup is to also provide highly available databases, this is not this should not satisfy you. This is not what we wanted from our infrastructure. So we decided to work around it. Also, but we still use stateful sets. And in front of the stateful set is a service that routes connections to the primary node. The service accepts connections from the clients and only routes connection to the master. We can also have another service that routes connection to the replicas. We have Spiro as a Docker container. We basically have a same Docker container that is used in AWS and in Kubernetes, because this container already accepts configuration in with environment variables, so we didn't have to do any work to adopt it for Kubernetes. And we also rely on Patroni to do failovers. And we use secrets to store database usernames and passwords. So essentially, for deploying things manually, we would have to deploy several manifests, one for the stateful set, one for the service, probably one for the secrets, and one for some other objects like pod disruption budgets. And the downside of that would be that there is no way to bind all these manifests together as part of one Postgres cluster. There will be still different deployments. It's easy to make mistake. It needs to, for instance, the cluster name needs to be written in many different places. So it would be quite a lot of manual tasks to just do this straightforward by running things, by deploying things manually. It wouldn't scale for our for what we wanted to build. So we tried to automate it. The first approach to automation is Helm. Helm is essentially bash scripts for Kubernetes deployments. So instead of writing things by hand, you just write a template, and in this template you define some variables, and then you, in your manifests, you also write those variables, and when the Helm deploys your manifest, these variables gets replaced with values. There is a Helm template for Patroni on somewhere on GitHub. And we tried it for a couple of databases, but it was also not what we wanted. It was still quite a lot of manual tasks. It required the special part of Helm called Tiller to be deployed in your clusters. It didn't support, so once the cluster is deployed, Helm is out. So when you want to update parts of your cluster, or when you want to repair your cluster in case some of the objects went down, it is not possible without manual interaction. So Helm did not provide the level of automation that we wanted, and we dug further. And we stumbled upon the blog post by the CoreOS that introduced the notion of Kubernetes operators. Basically, in the Kubernetes world, an operator is something that defines custom resources. Custom resources are defined by the YAML manifest and are translated to whatever you like. This is your task to actually react to this YAML manifest and deploy something. And those custom resources are watched by the controller that you write. And essentially, CoreOS introduced the operator for etcd, which watches the etcd custom resource, deploys it, and makes sure that etcd works reliably on top of Kubernetes. And we decided, why wouldn't we write some Go and write the same thing for Postgres? And actually we did. So what we came with is called Postgres separator, Zalando Postgres separator, and it defines a Postgres custom resource, a custom YAML manifest. Once this manifest gets deployed to the cluster, the operator picks it up and creates all objects that are necessary to run this cluster, including stateful sets, including services, including pod disruption budgets, including secrets. And it allows updating this manifest, and in reaction to these updates, it actually updates the cluster. So if you, for instance, want to change Postgres configuration and update this in the manifest, the operator will pick up this update, go to the actual Postgres pods, and call the REST API of Patroni to change the given configuration. And if this requires restart, it will also restart your pods, and will also do restarts in a very smart way. So instead of just killing your primary pod, it will first do the failover from the primary to the secondary one, and then first it will restart the secondary pod, then do the failover to this restarted secondary pod, and then restart the former master, minimizing the amount of time the service is down. So basically the whole idea of the operator is to encapsulate the knowledge of the human operator in the product, in the application that you built, and this is exactly what we did. It also creates databases and users for you, which is super convenient for our feature teams because they don't have to connect to their databases to do all of this. Instead, they just release these users and databases in their manifest, and this gets created by the operator. And it periodically scans the whole cluster, and when it figures out there is kind of a discrepancy between what is written in the manifest and what is deployed. For instance, someone went and deleted the stateful set, then it can repair things. So it basically synchronizes objects that are in Kubernetes with objects that are with the state that is described in the manifest. And also it's doing smart rolling updates, as I said. So if you need to restart all pods, it minimizes the amount of time when the master is down. It's also open source, not surprisingly. You can have it on GitHub, and we also worked quite hard to get a good documentation on how to deploy it. So nowadays, quite some companies also looking at this, and we have some reports of people running these at least on stage environment in their own setup. For us, we run both staging and production databases using the operator. We have, in the first number, there was the number of clusters that we had. I don't remember it by heart, but there are more than 10, definitely. Kubernetes clusters that are running production databases. We have one big staging cluster that are running more than 100 databases as staging. All of those is managed by the Postgres operator. So this is how the manifest looks like, and this is what our developers have to write. This is basically everything that you need to write in order to get your database up together with your application. So this is usually part of the development folder that gets merged. There is a pull request that gets merged, and then the CI/CD system automatically rolls out everything that is in this pull request, and the database looks like this. So we have a name of the database, which is quite important. We have the name of the team that is creating this database, and the name of the team is translated to team members, and those team members are created automatically for the cluster, so you never have to log into the cluster and create human users there. You have number of instances, which is 2 in this case, so you get a master and a replica with automatic failover out of box. There are some users described, and there are also some databases owned by these users, and there is a Postgres version that you need to roll out. So for instance, we are providing Postgres 11. Even Postgres 11 is currently in the beta phase. We are providing this for our users for staging environments to test. So we can roll out new versions very quickly by just updating our Docker image. And the whole thing looks like a piece of cake. It's like rainbow cake. You have on the highest level, you have the operator that starts the Spiro Docker image. Make sure that it configures environments for the Spiro Docker image, and then make sure that all objects that it created on Kubernetes are in sync. Spiro Docker image generates Patroni configuration, and then Patroni starts either inits Postgres or joins the cluster, creates all rows, makes sure there is only one master at a given point in time by basically providing these automatic failovers, and also changes endpoints to point to the master. So at every given time, clients go to endpoints. Endpoints have the address, and this address always points to the master. So this is done by Patroni, and we rely on all this stack. And all this stack is open source. We don't hide anything, so you can actually try it on your laptop or try it in your stage environment. And this is how it works for us. There is a database deployer who deploys the manifest, basically merges a pull request. This pull request comes to in the form of custom resource definition to the Kubernetes cluster. The Postgres pod listens for these manifests, finds out there is a new one, and deploys new stateful set, endpoint, and service. It creates cluster secrets where it puts passwords for the database users. So these passwords are never known to any of the operators, and they actually never leave the Kubernetes cluster. The operator creates those services, and applications that run in the same cluster just read those secrets and connect to the database directly. And also it manages on some other objects like infrastructure roles that are cluster-wide objects. For instance, we have a role that we use for monitoring, which is the same on all clusters, and it reads those rows and creates those rows on all clusters. So the operator is also a tool to ensure that certain invariants are the same for all Postgres pods that we are running. And one thing that I described is that Patroni actually is dependent on etcd or Consul or Zookeeper. And we had to get rid of this dependency because running etcd in Kubernetes is a pain. Etcd is a system that requires you to run, it requires the majority of the nodes to be always available. Otherwise, etcd comes into read-only mode without, and you won't be able to recover it unless you do dump restore. In Kubernetes, it often happens that some of the nodes go down, some of the nodes go up, especially when your infrastructure team updates your Kubernetes cluster to get to the latest and greatest. That is a problem, because if your etcd goes down and your Patroni depends on etcd, then all our clusters go read-only, and this is something that we want to avoid. So we thought hard about that, and Patroni in etcd looks like this. There is a etcd cluster that there is a Postgres cluster that is characterized by keys. Where is my clicker? Here. So there is a leader key. There is a members, which lists all members of the cluster. There is a configuration that is global for all clusters. There is a leader uptime, which contains the current position of the leader. And this is what is inside the keys, basically YAML that describes each individual members, how to connect to them, what is their state, and so on and so forth. So there is one thing that we used, is that Kubernetes is already powered by etcd. So why would we deploy the second etcd? But we could not just use the etcd that powers Kubernetes, because no one will give us access to that, and it's actually a bad practice to give access to Kubernetes etcd to someone else, to some other service, because if you get access to that, you can actually change any kind of everything inside Kubernetes. You essentially get admin rights on it, and this is something that we didn't want for our databases. But the insight was, why don't we just use Kubernetes objects themselves to store keys? We have members of the clusters that are running on pods, so let's use metadata in the pods to store member-related information. We have endpoints that have a property that they are changed atomically, so let's use an endpoint to store the information about the leader. And we can also use endpoint metadata to store configuration of the cluster. So there came Kubernetes support for Patroni, which has been developed last year, and we are currently using it in production. So we are using resource versions that are versions for Kubernetes objects that are changed when the object is updated, in order to ensure this compare and set operation. Essentially, if someone already updated a given Kubernetes object, its resource version changes. So if other client comes and tries to update it with the old resource version, the update doesn't go through. And this is how we emulate this compare and set. There is no, unfortunately, a TTL in Kubernetes, so we have to use soft TTL, essentially memorizing where the given key has been created, and then after the TTL expires, deleting this key. But this is not a problem in practice, and this is how it looks like on Kubernetes. Oh, that is too early. We have the pods. Inside pods, we have these inside annotations. We have the information of this specific pod, the same one that we had in the members key, what is the connection string, what is the state of this pod, and so on. Inside the endpoint, we have the information about the current leader, essentially the name of this current leader that is translated to these members. We also have the cluster configuration, basically storing all the configuration of the cluster that is applied to all nodes. And we have the initialize key that indicates whether this is a new cluster that has to run an EDB or whether this is an existing cluster. So all of this is stored inside Kubernetes and basically works without any additional etcd deployed. So now the interesting part, I want to show you the live demo. And first of all, let me log in into the test cluster in this console. Good. And here I want to get to the point where I can get the interface. Yes, so it's probably quite tough because the UI is not scaling up to this resolution. So this is how the cluster manifest looks like. This is our UI for deploying things. It's unfortunately not really designed for this resolution. It's not showing things properly, but let me try. Here I can just try to create a cluster, atmosphere test. I say default namespace, team ACID, version 10. I want to have at least 2 instances. Let's have some users, robot and databases, sample, something like that. And the owner will be robot. Yes. I can also say requests and limits on how much CPU and memory I want to give to a given cluster. I can click validate. Hopefully it doesn't give any errors. Good. So now the interesting part, I can just say create cluster and something happens. It says create request was successful, and now the creation of the objects are pending, stateful sets and Postgres manifests. So let's take a look at this cluster in Kubernetes itself. I can just say that. Can you see this text on the last rows? Yes, good. Get pods, and then use the labels in order to filter pods of the given cluster. ACID atmosphere test. Oh, I think I used an extra slash for that, so let's remove it. Take some time. Let's see, here it actually claims that everything is created, so it gives us, it created the manifest master service and says this is the URL that you can use internally from the cluster to connect. So yeah, here we have 2 pods. One is running and one is creating. Let's take a look at their roles. I just add another label that is called spiller role. And let's see. So this pod is a master, and I can take a look at site. Just select and see what Patroni is giving to me. Oh, yep, there are 2 containers actually. The other container is the scalar for shipping logs, so I have to say which container I'm using. Okay, so now it's saying here I am the leader with a log, which means that this node has acquired a log and it is running as a primary node. Let's take a look what's going on afterwards. Yeah, seems to be that it is running a database. So before that, Patroni started, initialized the database, created all the extensions, did bootstrap, and now it is running. Let's take a look at other pods. Yeah, the second one is also now received its role, it's a replica, so we can also pick inside. Yeah, same thing, we have to provide the container name. Yeah, and we can see that this pod actually bootstrapped here it says trying to bootstrap from the leader, so it found out that there is a leader in the cluster, bootstrapped itself, started as a replica, and now I'm saying I'm a secondary, I'm following a leader. So what we can do is to get inside one of the pods. I can just do exec. I will just do exec now, but in the cluster environment you can also connect from your running application. And I will exec into the Postgres container and connect to the database. And first of all, let's see if this is indeed a master. Select I will use PGs in recovery for that. Oh. Well, how comes? Yeah. Select PG is in recovery. Ah, too many things. Sorry for that. Good. So it's not in recovery, which means it's a master. And then we can also look at the databases here, and we can see that there is a sample database created by the robot user, and there is a secret in the cluster that is containing this robot user password, so the user application can immediately read this from the secret and connect using this user to the new database. Let's return to the presentation. Basically, here goes some reasoning of should you run databases on Kubernetes or not. One of the authors of famous Kubernetes books, Kelsey Hightower, who is also a very prominent community member, said at one point that if you're considering running databases on Kubernetes, just consider managed service like Amazon RDS or Google databases. Don't run things inside Kubernetes. Well, that would be probably for many people a signal that what we are doing is crazy. But on the other hand, that happened like 1.5 years ago, and since then a lot of things has changed in Kubernetes, and there is a very strong community interest in running Postgres databases on top of Kubernetes, and this is manifested by the number of projects that are spawned. So there is our operator, there is another product from Crunchy Data, which is also open source. There is Red Hat Project Atomic, which we are working closely with. There is a KubeDB, that is another project to run many different databases on Kubernetes as operators. And there is also a project Habitat that tries to make a lot of things like we are in Patroni, and basically try to do leader election in a very abstract way. So people are really looking into running databases on Kubernetes. And what kind of benefits does it give to Zalando? First of all, it allows us to save money on staging databases, because we can easily pack multiple staging databases on one node and save money compared to RDS. But this is not all. We can have as a real super user, which allows us to do a lot of interesting stuff like doing dump sol. We can stream our data from our database somewhere else using logical decoding. We can have a lot of custom extensions that are not available in AWS. Actually, AWS supports logical decoding, but the only extension they provide is called test, which doesn't allow you to do anything. For us, we have a lot of extensions there. And we can, for instance, use a local storage on i3 instances that is completely not supported on RDS, which gives much higher performance numbers for us. So there are quite a lot of things that we can do with our custom setup that we could not do by just using a managed service. There are other things as bonus projects. One bonus project is called BGMon. I mentioned initially that the Postgres database is extensible, which means that you can easily write your own custom server process. And we actually did this. There is a custom server process that gathers the monitoring from the host, like a top-based system. Gets both Postgres monitoring and system monitoring, and returns it as in a REST API. So we use this in order to base our monitoring on. So we don't have to install anything additional like Prometheus or something. Everything is already inside our database in the form of this custom process. And not surprisingly, it's also open source. It's on GitHub, and you can take it and can use it. The very cool part that we have is a system to authenticate human users. Initially, we had to go through LDAP in order to sync human users that are defined elsewhere with the human users that are defined in the database. We had a script that runs every 1 hour that does this. Probably a lot of you also doing something like that, and it's error prone, it's ugly. It doesn't solve the problem of passwords because the password still has to be generated and somehow supplied to the user. So we were thinking hard about how to solve this issue, and we also run OAuth inside the company, and all authentication is based on OAuth. And we thought, how would it be cool to actually marry those two technologies? How would it be cool to make Postgres database go to the OAuth endpoint, authenticate itself, and then permit you to log in? And this is what we have, because as I said, Postgres is extensible, so you can have authentication that is based on PAM, pluggable authentication modules, in the ecosystem that is there in Unix systems. And we wrote a custom PAM module in C that goes to a given OAuth endpoint, passes the token that you get from the user, and allows you to log in if this token is validated. So what we essentially get by employing this is very, very strong, very, very big one-time passwords that are automatically rotated every so often. For us, for instance, every hour. The password is actually so big that many tools that try to work with Postgres does not accept it, because they have a very limited, they have a limited field of Postgres passwords, which is usually limited to like 250 characters. And the OAuth tokens are, I think, around 880, 280, 300. So many tools just doesn't work with this system. But this is the problem of the tools, not the problem of the deployment, not the problem of the solution. And we don't store any super user credentials anywhere to rotate those passwords. Those passwords are rotated automatically by the external system. Postgres just goes to the external system with a token that user generates on their computer with a special tool, supply this token as a password. Postgres goes to the external system with this token, gets yes or no, and if it gets yes, permits the user to log into the database. So we automatically create team members in the database and allow them to automatically authenticate. And this is the project that is also on GitHub that you can also use for your own environment. For that, we have to put this line in the PGHBA file that says that all authentication for the given group has to go through PAM, and we create users in this group. And there's quite a lot of work in the open source, and this has been possible by many people. Some of them are working for Zalando. They are my marvelous colleagues. Some of them are not working for Zalando. Some of them are not working for Zalando anymore, but we are still kind of a community that get together and actually work on the common goals and help each other in deploying those projects. So those are good people that made it all possible in and outside of Zalando. And basically this is our philosophy, to hire great people and get out of their way and allow them to do good things. And the interesting part is that we are still hiring. We are hiring database engineers. So if you are in the mood of moving to Berlin, which is a nice city, and start working with Kubernetes and Postgres and do crazy stuff and talk on conferences, then here is a link, or come to us, or come to the Zalando website. And given that, if you want to rate this talk, I would appreciate this. There is a link in the application, in the conference application, so you can rate it using that. And given that, thank you very much, and I think we have time for a couple of questions.
Hi, great talk.
Thank you.
At one point you said that you got rid of etcd and you moved to the labeling in Kubernetes or something like that. But with etcd you solved the problem of master election, leader election. So how did, because then you had the same problem again. How did you solve it?
We get rid of etcd, but we basically replaced the functionality of etcd with the objects that are inside Kubernetes. We didn't get rid of the concept, which is to use this distributed consistency system to facilitate leader election. But this distributed consistency system is a pluggable module inside Patroni. You can use etcd, you can use Consul, you can use Zookeeper, and now you can use etcd to do the same task. You basically have an interface that has to perform certain operations. It has to acquire the leader key, it has to try to acquire the leader key and fail if the leader key is already there, it has to be able to update members and do something else. So if the system satisfies this interface, then it can be used in Patroni. And one of the implementation of this interface is Kubernetes, which we actually use. And this is basically where we store all this metadata. Yeah.
It's working. First of all, nice presentation.
Thank you.
And I've got a question about Patroni. In context of incoming, I don't know, the status of this project, master-to-master replication in Postgres, you know, and do you, what are your plans to in Patroni, you know, to emerge some code from BDR project?
Mm-hmm. So the question is, do we want to support master-master replication in Patroni, specifically by using BDR? And the answer is no, it's out of scope. BDR works, it's kind of bi-directional replication, because you can write to different Postgres primary nodes, but they don't have a consistent transaction snapshot, so they don't know about each other except that they asynchronously moving data from one point to another. So it's not enough to have a proper multi-master, and we did experiments with BDR like 2 years ago. Even I have a experimental branch somewhere on GitHub to integrate Patroni with it. The problem is it's really hard when BDR node goes down to restore the system to the original state. If you have 3 BDR nodes, one node goes down. If you want to get this node back, usually what you have to do is to have a full dump of your whole database to this node. And if your database is any way big, then may take a lot of time, and it also may impose quite a huge load on the master. So it's much harder than with the normal streaming replication. One of the issues why is that in Postgres, logical replication, which BDR is based on, does not work correctly with physical failovers. If you do a failover, then you cannot continue streaming in your logical replica from the same position, because position is not stored over failovers. This is something that Postgres community has to address in one of the new versions. If it is addressed, and BDR will be easier to recover to the state once one of the nodes went down, then we will definitely look into using it and supporting it in Patroni. But actually, since Patroni is an automatic failover system and BDR does not require you any failover because all of the nodes are available for writes, maybe Patroni is not necessary if you decide to use BDR.
Okay, we are out of time, but if you have more questions, do not hesitate to ask Alex after. So thank you once again, Alex, for your talk.
Thank you.